老师刚刚是觉得，然后他自己写词，
因为上面我记得这组
那我在这看。
When extra force is exerted on the surface of the computer, the projectile is ejected at a high speed. Investigate this effect and the parameters that affect the ejection speed. is the process during the ping pong ball was ejected and the relevant parameter that affect the ping pong ball ejection speed. And there is our experience setup. We use the measuring ruler and we use the iron ball to play the ball one that will hit the surface of the ruler, and there's the iron ruler, and the table tennis ball will be our O2 that will be ejected from the ruler. And we use the lighter frame to coating the rod so we can fit the hitting force and hitting point. And there's about our observation. We will talk about the definition and the process of the ejection. And our definition of the ejection speed, we will make sure that ejection speed when the O2 is one side of the ruler. And the process of the ejection, you know that when O1 be released and apply force to the ruler, now that there will be the different point of the O2 place will also affect our experience data. So and the relation between the supporting force and the deflection of the ruler, we can use the beam deflection formula to explain this. And next part, when the ball one hits the ruler, there will be the deformation of the ruler, and the ruler will absorb the elastic potential energy, and for the ball two, there will be the kinetic energy of the ball two and the rotation connecting energy of the ball two. So in our experiment, we use three factors to get our manipulated variable. First one is the position of the ball two and the mass of the ball two and the force exerted by the ball two on the ruler. And there's our theoretical model. I will talk about the force analysis and the beam deflection formula and the energy analysis. About the force analysis, because that in our experiment, our ping pong ball when they're ejected, it will also rotate. So we use the force analysis to explain that why the reason that the ball will rotate is because that when the ball one hit the ruler, there will be the normal force from the ruler. So and because that N1 will bigger than N2, so they will have the torque to make the ping pong ball rotate. And the clockwise and the counterclockwise will depend on the value of the N1 and the N2. And there is the beam deflection formula. Then this formula that we can explain that what is the supporting relation between the supporting force and the deflection of the ruler. And we can know that when the A is bigger than X, we can use formula 1, and when the X is bigger than A, we can use formula 2. And in our experiment, because that A will be equals to the X, so we substituting A into the equation, and we can know that Y will equals to this. So we can use the data that to get the slope of this change, and we can know the deflection, the relationship between the place that we place the ball one and the deflection of the ruler, and we will get this slope. And about the energy analysis, we can know that the work done by the ball one and the initial elastic potential energy of the ruler will equal to the elastic potential energy of the ruler and the kinetic energy of the ball two. And so we will get this energy conversion equation. And we use beam deflection formula to rewrite it. And we will get this new formula. And finally, we can know that the V1, and we will get the theoretical equation that can be our theoretical curve in the experiment to compare with our data. And there's our next, we will talk about the experiment data. We use the fielding weight and the release height to be our manipulated variable. And the first one is the weight of the particle, and our control variable is the position of the ball placement, like this. And the iron ball impact force and the contact surface material. And in this data, we can know that the change or the data will decrease. And that is because that when the N2 increase and the velocity of the ejection will decrease, and we connect it with our theory, with our theoretical curve, is because that the denominator, when it's increased, that velocity will decrease. And second is the release height, and there is our experience data, and we can know that we can find that when the release height increase and the ball one ejecting velocity will increase. That will because that when we increase the highest, the velocity will increase. Then connect with our theory. And about the discussion. difference is same. And step 7, 10, and the difference between this is the same. But in our data, that these two data points is relatively close, and we will want to discuss the reason. And so we would like to find this reason. So we turn back to our theoretical curve, and we consider the initial elastic potential energy. So and we consider this term our integer that can tell us the deflection of the ruler. And we use Python, and we use the projective function to get this, to fit the equation of the ruler shape, and we get this chart. And we can know that the difference in the area under the curve between the 30 centimeter and the 10 centimeter is smaller than the length between the 7 centimeter and the 10 centimeter. So we can find out the result that because this two one is relatively close, so the elastic potential energy will elastic close and normally close, and so our data points that these two data points will relatively close. And we want to also discuss that why our theoretical curve is bigger than our real data. So we consider the rotating because it will make and there will be the energy that transfer to this. And so we calculated K is equal to the experimental measure total kinetic energy and plus the rotational energy, and divided by the theoretical kinetic energy, and we get this chart. But about the energy transfer efficiency that is smaller than the 20%. So we can know that most of the energy are consumed by the friction or other factor. And we can also know that because that impact of the different bolting capacity is not really similar of the temperature is smaller than. So we can know that, and there will also the reason why this one is relatively close. And we talk about the energy loss, about the bound of the ball one, and we can know that the release height of ball one increase, the ball one velocity will increase, and the energy loss will increase, and there will be some kind of energy loss. And we consider the parameter deformation of the ruler, and just like this, we know that the release height of the ball one increase, the permanent deformation of the ruler will increase, and that will cause the energy loss increase. And there's our experiment. We make sure the energy loss. And why the trend become flat? Because that we use the vertical curve, and our excited result is just like this. But our real result, the trend is relatively flat, and we will want to talk about the reason. And we find the reason that we consider the deflection of the ruler, and because that they can divide it into two parts. First part, the deflection of the ruler will be the liner elastic ruler, and next it will be they will be hit the situation because of the plastic deformation. And we can know that the point that we can divide it into two parts is that the hanging weight is bigger than 100. And in our experiment, the mass of the board is about like 300 grams. So the end of the ball is bigger than 100%. So it will make the ruler non-linear elastic region. So the elastic potential energy will be the situation. So it is the reason that why the data trend is relatively flat. And here's our conclusion. In our data analysis, we can know that the potential energy of the iron ball and the elastic potential energy of the ruler will equal to the work done by the ruler's restoring force and plus the kinetic energy of the ball tube. And we transport this equation, and we can finally get the equation, and we can have the theoretical curve and get the D1 to compare with our data. And another factor to affect the result, we get that in our experiment, when the release height of the ball one increase, the ejection the ejection speed will increase, and the mass of the ball tube increase, the ejection velocity will decrease, and the initial deformation, when it increase, the velocity will increase. And about conclusion 2 part, and we talk about the discussion. We find that the reason that the tensor, we use the different position that we put the ball tube, and the reason why the 10 centimeter and the 13 centimeter are close is because that we fix the deflection of the ruler, and we can know that the numeric post and the V1 will be post. And about the reason that the experimental and theoretical values are different is because we consider energy loss about the rotation of the ball and the permanent deformation of the ruler and the cell, and I think that will be the friction that will affect the data. And thank you for your attention.
Thank you for the presentation. And the first question is, did you consider the deformation of the ball?
Yes. No. We just consider the deformation of the ruler.
And the next question is, how can you ensure that your ball one is thrown in the same position?
In the same position, we use trigger and we use the rulers.
Okay, thank you. And the next question is, you say you consider rotate is the effect of the error between theory and the data, right?
Yes, but we consider it as an energy loss.
So did you consider the direction of rotate?
No.
Okay, thank you. And the next question is, did you consider the ejection of the ejection direction?
Ejection, no.
Okay, thank you. And the next question is, in your observation video, I just see one ruler is blank. Do you think is suitable to be the setup?
Yes.
Why? Could you please explain this?
I think that our setup is fixed.
Okay, and what is your error bar? How can you calculate your error bar?
Because we error bar is that because we conduct our experiment many times, so we will get an error bar that there will be a little different. But I think that maybe it's caused by the friction.
So, in your theoretical and your data, did you consider any? Did you have any qualitative analysis on it?
Yes, I use the discussion to connect why the data will.
Did you qualify the amount of your error amount between the data and the theory?
No, I think that is because of the friction.
Okay, thank you. The chart on the what was the
Thank you.
long projectile, such as a plastic ball or so on, is inserted between them close to one of their ends, and an extra force is exerted on the surface of the lures. The projectile is ejected at a high speed, so I think high speed should be defined, and investigate its effect and the parameters that affect the ejection speed. So the main focus might be the process during ping pong ball was ejected, and relevant parameters affect the ejection speed. And the overview is the first one is phenomenon and setup. The definition of the ejection. The ball is the projectile in the promised statement. Like this projectile is a ball two, and ball one is the extra force. And the theory. The first one is the force analyze. The first one is normal force and friction, and being diffraction formula, and rotation is torque, and energy analysis energy. So the reporter consider the energy loss like the rotation will be used to the energy loss, and conservation like gravitational energy and elastic energy. And the third one is experiment. The weight of plastic ball and the weight of plastic balls increase. The velocity also increase. Release height and initial height increase. The velocity also increase because the force might be bigger. And the quadratic function by Python because they do this yes. And elastic energy is numerically close. And the kinetic energy is close. And energy loss, ball one height increase, which causing energy loss increase. And the rotation friction also causes the energy loss. And the train becomes nonlinear elastic region. And here's our discussion point. The first one is energy transfer because the reporter considered the energy transfer between gives rotation because when reporter talk about the energy transfer, they say the rotation causes the energy transfer because while rotation they may use the velocity. And the next one is shooting position, and the shooting position should use 7, 10, and 13 centimeter position. But I want to ask if the reporter has the minimized shooting position. And only 3 differences is the shooting position and rotation energy release. And the different situation of 102 and 102. So I would like to invite the reporter on the stage. So the first question is in the prompt statement. So please send your prompt statement. So the first one, the prompt statement says usually use 2 balls, right? Yes. So what do you think if there's one ruler and the other one is on the table? What do you think? They might be different. Because like this one is the table, and this one is the ruler. And what is different between this setup and your observation? What is different?
I think that our experience setup is fixed this problem statement.
Yes, but I want to ask, the first sentence and 2 rulers, so
We use 2 ruler, but the ruler 2 is this.
yes, I know, but what's different between here's table and here's ruler? Because the problem statement said 2 ruler, but I think there's table. There's almost the same with there's table.
No, because the friction will be different.
Friction.
The friction of the table and the ruler is different.
So you say
So we use 2 ruler, and this fixes the problem statement.
okay, I see. So next question. The next question is you use rotate to consider your energy loss, right?
Yes.
Could you please show me that?
Yes.
So the first one is rotate because this one is your for your energy loss by fix the model because you have to fix model after you do this. So
Yes.
you have that.
But I think that the rotational, we just calculate the real rotational function, and that is because of the torque, and we can know.
Okay, I understand, but I disagree because I think there might be conflicts. So the next question is the position because in this is right. So what do you think? What is the minimum minimum position of this one? Might be 5 or what is the minimum? Because when the position inside is if this one is good and this one is the other good. So and is the one more. What is this one? What is this minimum position? Is your lens here?
I didn't think that we should consider.
Yes.
But I think that because we just use the 7 and 10 and 6 centimeter, but I think that we can it can be explained by the big diffraction formula.
But what is the minimum position? What do you think is here? Because yes, just 3 data, but we cannot use this one to calculate the to have a conclusion or to have a fixed function of this. Do you agree?
No, I think that is not important because that I can put it in a different way, but we the place that you place it, we can also use the link diffraction formula to explain that and to find a relation between the supporting
So
force.
what do you think the force here? Because if the position is different,
Yes.
the force might be different, right?
Yes, right. So we use the Bing formula to find a relation between the supporting force and the deflection of the lunar. And we finally got I think that can we calculate the force that different.
Okay, so but I disagree because I think there might be the minimized ingress place that the ball can be
Yes.
extract, right?
But that is our control variable in our experiment.
No, there's a
And we use the 7 centimeters, 10 centimeters, and 13 centimeters.
But I think I want to know what is the minimum, or you didn't did the experiment about.
So what do you think that what is the minimum?
I think in your okay, so I think in this experiment I don't know what is the coefficient of your friction, so I cannot know what is the minimum. So in page 13.
Yes.
So next question is in page 13. Why this one is almost the same and this one is almost different?
When you say that this one is relatively close,
Yeah,
this one
is very far.
Yes,
and
I-
this one is close. So
this
what is
one,
one?
this 2-1,
This 3-1 because this one you said this 3-1 is theoretical
yes.
model one, and this one is your data. So this one is almost the difference, and this one is almost the same. So can you explain that?
Oh, okay. So because that theoretical line is pretty, it could be hit by the blue theoretical line, but in the theoretical line, the tangent line is closer to the 30. So that's fixed.
So do you have fixed function about this one?
Fixed function.
Yes, because you have to fix your function after the data is here. So do you have any function about? Can you explain this?
Yes, we use the there is our theoretical
formula.
the theoretical curve, and we find the trend of these 3 data, and it will decrease.
Okay, so I think this one is why. So this one might be your experiment. Is your function, like this one, like after below data usually.
I consider the work done by the O1, and this is the energy transfer equation, and we transport this, and we use the deflection formula to rewrite this, and finally after the transporting we get this theoretical curve.
But I think you should make a fixed function after you make, because you have to discuss the parameter about the
Yes.
right. So
But the parameter is this, and this is the height.
this one is your theoretical model, but you have to okay, so you have to fix function. So
Yes, I have.
no, this one. No, this one is not data because you have
Yes, but I have the data and I connect it with the theory and the strength of the
show me.
Yes, I also.
No, this one is almost this one is the same with the previous one, right?
Sorry, I
Oh, okay, so next question. You said rotation, right? Yes, but not rotation, so it's replace the ball on the, you inject the ball on the ruler. One is on the table and the other one is has the angle, right? So what do you think the ball might be inject? Is a parallel one, or it will be like not parallel to the initial velocity direction?
I think that will be parallel.
No, I don't think so because when yeah, because in this one, the ball might be here, and the injection you place the force here, right?
Yes.
And there is no other force to have the vertical force. So the ball might be from here. The initial velocity might be from here, right? You agree?
But I think that I use the force and the analysis is. I use the force analysis to explain the injection process and.
Yes, I see. But in here, in this one, is N2, right? So there's no other force to resist it from
This
this
force,
right?
I think that the force will finally.
Yes, it will not be because you have Fk here, and here and this Fk and this Fk is in the same.
Hey, time's up.
Thank you.
So your opponent please summarize.
So the first one is one or two ruler. This problem. The reporter used two rulers to make two surfaces the same, and within the deformation difference caused the horizontal projectile motion or projectile motion. And the rotation energy is just calculates the torque and go to projectile position. We think there's a minimum position that the ball will and I also think the reporter should analyze it and instruments of different ways. Reporter just explained this theory result but no analyze of the parameter because they didn't fix the function of that. And here's injection direction. The reporter think is parallel, and I think there's an angle because there's no other force to place its to reset it from this side. So here's all of my summarizing.
Okay, so first I'd like to ask about the reporter. So can you interpret the problem statement? So as in the problem statements. So can you play the video? So in the video that you play the video. Yeah, we can obviously see that the ruler is shaking. So maybe did you consider it as an energy loss because the energy will transfer into the energy will transfer to make the ruler shaking. So
Yes,
maybe it's an energy loss, but you didn't.
Yes.
So you can
Yes. I say I consider the deflection of the ruler and.
Okay, so in that I would like to ask about the number of how many times you do it once every experiment. How many times do you do it?
Many times we find 400 of those.
Yeah. So have you made so you mentioned that every time the ruler will have terminal deformation, right? Right. So do you agree that every time the ruler will permanent deformation?
I don't think so because there is bending
Okay.
after.
So if you mention that, so did you actually measure all ruler of the young mothers of your ruler? Because we can maybe different ruler the young mothers won't the same. Did you measure it?
No, the young mother, yeah, that's the big.
So did you measure it? You didn't.
Yes.
So but you did show. So maybe you
Yes, I showed it in the green deflection formula. And this is about.
Okay, fine. And next I would like to ask about the reporter analysis. Is that so that the ruler so that the ruler is first is associated as an L and there's an A right. However, when you just when the ruler bends, it will transfer into so you but the A will transfer into here and the L will transfer into this. We're seeing the L will like the A and L will change. So do you think it will affect the calculation of your
But we can measure the ejection speed that the force starting to eject. So.
yeah, but I think that this may impact your theory.
Yes, but we consider the deflection of the ruler. And we calculate it.
But
We
you're
get the
in-
data.
yeah.
We get the data.
Okay, fine. So next I would like to ask about the ejection condition. So it's always the forward ejection.
Yes.
Okay, so and is there any optimal ejection condition? Like when the optimal ejection condition, like when the ball will kind of maximum.
In our experience, no.
Okay, can you explain the reason why this is linear results with verification?
Linear.
Why this is linear with verification?
Time's up.
Okay, fine.
Thank you.
Okay, hello everyone, I'm a reviewer from Premax. So today I will review the lure cannon. So first is this is the point statement. So the main point is that it will have a round projectile and it will close to one rear end and try to add an extra force. And we have to in fact try to measure the different parameters and of the ejection speed. And that is summary of reporter. Reporter, the third part is they have this talk about the bending of ruler and anti-refractic and the base theory. And the experiment they have used the drop mass from height, the position of ping pong ball, and the release height of the ball. And that's the reverse script. We ever have control the instrumental setup and have to lots of quantitative explanation for ejection, have quantitative verification of qualitative theory, and have qualitative comparison between the theory components as well, and have various parameters, and it's a certain aspect of the definition between theory and experiment. The suggestion is that the theory did not fit the different data, and they didn't defend the deviation in the theory, and they did not consider energy loss in the theory, and they incomplete explanation for the energy loss. And they could compare impulse instead of drop heights. And then the summary of the opponent. The opponent focused on the deformation of the ball and the deviation of theory from experiments and the error bars and the quantified amount of error bar between theory and experiment and definition of high speed and the number of parameters and the energy loss from the vehicle. And next is the discussion. So the opponent asked about the deformation of the ball and the person said no. And we think that there will be a deformation of the ball, but it's likely. And that is the opponent asked about different from the experiment, and this reverse the spin of the ball, and we see that it's due to they also have to consider energy loss. And next is the opponent asked about this have to they lack some charge lack of error bar. And next is the opponent also asked of like they don't use the ruler to change into the table, and the rule say but it has to. It is also the same because we have to make sure the friction. So we agree with the reporter that it is sensible. And that is they say a calculation of work either due to the rotation, but the reporter didn't calculate it, and we advise that they should consider it. The next discussion, the opponent asks the the minimize of the ejection fee, and the reporter say they don't know because they say there is no minimized points. And we agree with the opponent. And that is the ball might eject horizontally, and the real estate force analysts they use force to analyze it. And we agree with the opponent they could consider conditions for the downward ejection. And that is our question to the reporter and opponent. So first I asked the referrer of the ruler shaking called energy loss. They just say they just consider the deflection of the ruler, but in the video it's apparently that the ruler was shaking the fast speed. So we can know that there will be an energy applied on to make the ruler moving, so there will be an energy loss that is considered. And that's always effect on it. They say yes, and the evaluate that they nature. And we think that due to that, what I just have explained, the A and L of their assumption will be changed when the ruler is deflation. And that is asked about the opponent that whether the ruler will permanent deformation for every ruler and not always. We agree with the opponent. We think that's won't always. So they have to measure, but they didn't show. And that is the point that they missed in the discussion. It's the permanent deformation of ruler and the method for the measurements and the source for the energy which the ruler is shaking. And that is the ejection condition and the optimization of the speed and the energy computation equation.
About the discussion time that the opponent asked me about the place that we place the O2. And I finally use the big formula and we calculate that what is the supporting force of the deflection of the ruler and find the relationship against the real data. And about the reviewer, he said that the energy transformed by the shaking ruler will also affect our data. But we consider the deflection of the ruler, and we finally get the data and considering about the energy cost. And about the reviewer, he said that our theory cannot fit our data, but I get the theory right and the trend of our data is the same. And I explain why these two is relatively close, and why is the theoretical proof is bigger than the real data is because that we consider energy loss about the rotation of the ball and permanent deformation of the ruler, and we finally got the data to prove that. And about the discussion, the opponent said that the place that we put the ball to will affect our data, but we use the beam deflection formula to prove that we calculate the supporting force and the relationship between the supporting force and how the deflection of the ruler, and it will affect the elastic potential energy, but we calculate that, and it will be the energy loss in our experiment. So I think that the data we use and the theoretical curve is fix our data, and we finally explain that why the why the data will like this. Thank you.
Any questions of the tutorial?
May I? Please come to the, this is the page. On the left-hand side, you have a low end, you have a data
Yes.
related to the theory and the experiment. Apparently, they have very big difference.
Yes.
Okay? And you mentioned the energy loss, but you didn't consider four terms: rotation of the ball, permanent deformation of the ruler, song, and friction. But you did mention these four things. However, I don't know which one is net contribution to the error.
We didn't get the data about the sound and friction rate, but we get the real data about the rotation of the ball and the permanent deformation of the ruler, and we show the data. This is the there is the permanent deflection of the ruler, and this is real data and about the rotational. This is the real data that we got the rotational conductivity, but we felt that the rotational will affect the energy loss.
My question is very simple. You raise four terms, right?
Yes.
I'm asking which one is more important to contribute to your error.
I think that is because of the deflection of the ruler.
Follow please.
The second one?
Simple.
Okay, I think it's a friction.
Friction.
Because
I think it's the deflection of the ruler and add the because the ruler is shaking, so there's also the shaking of there was also energy loss. Okay, it is two examples.
Thank you.
You see the ball one transfer all the rotation into the system. The ball one transfer all the rotation energy to the system. Because you use energy HR, right?
yes.
It means that this is the energy rotation energy of the ball one, right?
Yes.
And then the energy
No.
transfer to the system totally.
The initial elastic potential energy of the ruler because it will the ball is decided so it will also affect the energy.
Yeah, I agree with you because there is not 100% transfer into the ball. So this is why we mentioned that in the next discussion, we say they need to discuss the ratio of the energy transfer.
I think it's not all transfer. If the height is too small, the other resistance can be ignored. So if the some in some condition, in this condition, I think it will not be 400, but it's almost.
So page 22, just your result.
Page sorry.
22, 22. Or 23, 22. Just your results once more.
This
22, 23 are the same. 22. 23, right? So the top line is theoretical calculation, correct?
yes is the theoretical.
So your data is sort of just parallel, but just lower.
Yes. And we consider that is because
Tell
the
what's the percentage?
what is this?
Percentage. Different.
Different.
I mean, when you plot this kind of curve, it's very hard to really see what's going on.
So you read that
The difference, the percentage.
oh sorry because it's too small so this is
No, your theory and your experimental results. What's the difference on percentage?
去，不要打到学生的时间，可以到荧幕面去没关系。
是不会挡到吧？
你手可以举高，这不是问题。
So let's start with the bring of the water. So 6, 8, 8, 7, 6. And the opponent. 5, 8, 6, 6, 7. And the reviewer. 6, 8,